Behold the earth, teeming with life, ideally suited for the development of human civilization. It's no wonder that previous generations held the fundamental belief that the resources of the world were unlimited, that our planet, with its ideal environment for life, was provided for our benefit, and that we bear no responsibility for ensuring that the earth remains fertile for the development of our civilization. But as our population has grown, our appetite for energy has increased, and in some cases we have misused our land. We can no longer assume that the earth will remain eternally ideal for the advancement of our civilization or the quality of our life. Rather, we will forevermore be called upon to heed that biblical admonition. We need to be wise stewards of creation. But how do we know what to do? How does the earth really work? How could humans influence our climate or sea levels or any other aspect of the habitability of our planet? Fortunately, as our technological civilization has grown to where humans can affect the earth, we have also been provided with the tools to study the earth and understand it, predict its future, and determine the actions that will be most effective to protect our future for generations to come. In the early 1980s, we had been studying the individual components of the earth: the atmosphere through meteorology and atmospheric chemistry, the oceans through oceanography, the land and its biology through ecology. But the earth is more complicated than that. The atmosphere, the oceans, the biosphere, the cryosphere are all coupled with complicated feedback mechanisms governing their interactions. The earth is not simply individual components. It is an integrated system that we need to understand as a system if we are to predict the future of the earth. In the late 1980s, NASA embraced the concept of Earth system science by bringing to bear the most important resource for studying the Earth as a system: the global perspective of Earth that is provided by orbiting spacecraft. NASA undertook one of its most important programs, the mission to the planet Earth and the Earth Observing System, with the Terra and the Aqua and the Aura satellites as the principal observatories for studying the Earth as a system. Many satellites have been added to this fleet of satellites observing the Earth, and these satellites are and will continue to provide comprehensive observations from which we can understand the Earth and develop the models that allow us to predict our future. In tonight's program, we are going to celebrate what we have learned about the key components of the Earth system since we embarked upon Mission to Planet Earth some 3 decades ago. But as we celebrate all that we have learned, we need to be aware that we are in a race against time. The Earth is changing. Human civilization is influencing the Earth. We need the best possible scientific understanding of all the factors that will influence the future of the planet so that we can make wise policy decisions to protect and to preserve this planet on which our civilization depends, and if need be, adapt to the changes that will come. We need to become and forevermore remain wise stewards of creation. We begin this evening with Gail Jackson, who will discuss the water cycle that is essential for life. Then Lola Fadoyimbo will talk about the carbon cycle, which is driven by many events, including changing forest covers. And Thorsten Marcus will examine the key ice sheets of the Antarctic and Arctic and their role in sea level rise. And finally, Piers Sellers will wrap up with all the tasks that still lie before us. Gail?
Thank you. Our Earth is a water planet. From the oceans, ice, rivers, lakes, and aquifers, to the water suspended in our atmosphere, our Earth is definitely a water planet. Take a look at our lovely Earth. Did you know that 99.5% of that water is stored in our salty seas or locked up in glaciers and other inaccessible locations, leaving precious little fresh water available to support all life on Earth? So one of the vital signs of our Earth is the water cycle, and understanding it and knowing it will help us to monitor our freshwater resources. And we can do this by measuring where, how the water moves within our planet, and I will talk about that today. This is a cartoon of our water cycle. It shows the linkages between the surface water, condensation, precipitation, and evaporation. The water cycle is a complex system that drives the movement of water and actually heat and energy around our planet. Let's start by exploring the role of our deep and vast oceans in the water cycle. As you can see in this visualization of satellite data, the ocean surface temperatures are not uniform around the oceans. The warm waters in red and the cool waters in blue drive the movement of water and heat throughout the oceans, which can in turn then influence our weather patterns, such as might be seen during El Nino and La Nina years. Also driving the movement of water in our oceans is salinity, as shown in this visualization of Aquarius satellite data from NASA. Where evaporation occurs, our oceans get saltier, shown in red. Where precipitation falls, ice melts, or rivers discharge, our oceans get fresher, as shown in the blue. As the ocean water becomes saltier, it becomes more dense and settles down to the bottom of the ocean, and vice versa for the less salty water, which rises to the top. Taken together, surface temperatures, salinity, and also the ocean winds, the winds above the ocean, combine in a complex dance that drives the ocean circulation patterns, as shown here. The oceans also store massive amounts of heat and are very slow to release it, which makes them a major driver in our Earth's climate system. The oceans and the atmosphere actually work together. Without the oceans, the water stays on surface, and we need the atmosphere as well. For example, intense sunlight in the tropics causes evaporation from the salty oceans, and that water forms into massive clouds. Those massive clouds then are moved by the atmospheric winds to the mid-latitudes, where precipitation occurs either in the form of rain or snow. The only way to get a global perspective of precipitation patterns is to measure it from spaceborne platforms. 6 months ago, NASA and the Japan Aerospace Exploration Agency launched our joint Global Precipitation Measurement Core Observatory Satellite, or GPM for short. With 2 advanced instruments, the Core Observatory for the first time is able to measure all phases of precipitation, from very, very heavy rain to light rain to falling snow. The GPM spacecraft serves as an anchor to a domestic and international constellation of satellite partners, which collectively provide precipitation estimates everywhere in the world every 3 hours. In essence, taking the pulse of the planet's precipitation. This imagery shows one of the very first events measured by the GPM spacecraft. It was one of the late season falling snow events here in the East Coast on March 17th. The resulting 7 inches of snow in the Washington, D.C. area may have affected your St. Patrick's Day plans this year. Off the coast of the Carolinas, the high cloud tops are icy. Down at the surface, heavy rain shown in red fell in the Atlantic Ocean. Farther north, over land, the storm has much lower cloud tops, and they are composed of snow shown in blue, which fell at the surface. And we can see this information because the GPM spacecraft has 2 advanced instruments. One of them, which I like to call the X-ray through the clouds, measures the precipitation all the way through the cloud and provides what I would call an X-ray at the surface. It's a 2-dimensional view of the precipitation. The other instrument on board is what I like to call taking a CAT scan of the clouds. And it takes layer by layer within the clouds information about the precipitation that is vital for helping us to understand precipitation and weather forecasting and climate models. So we're very excited about this data. Where else but NASA, with our partners, are we able to achieve such success so early in the mission? GPM also uses its data for applications to provide societal benefit. GPM observes hurricanes and blizzards, but as shown in the top 2 panels here, we are also able to look at the conditions that might lead to landslides and floods. On the other hand, for drought and water availability maps as shown in the bottom 2 images, we need to know how little it has precipitated over time, and GPM can tell us that too. Emergency management then can use this data in near real time to make evacuation plans. Precipitation in the water cycle influences every person, every day, everywhere. Maybe one of the greatest impacts of NASA's data is its use in improving weather forecasting models and climate change models for our everyday lives and our long-term future. Now I would like to introduce Lola, who's going to talk about the pulse of our planet's biosphere.
The most visual manifestation of life on Earth happens every year when springtime comes and fresh green leaves and grasses appear all around us. The biosphere, our living world, is fueled by the seasonal pulse of energy that the change in season brings. In this visualization, we can see the seasonal changes to plants on land and in the oceans. Using data like these, we can estimate agricultural yield worldwide, predict famines, fires, and algal blooms, or help with land management. This global view of our biosphere is also crucial for studying the flow of carbon through the Earth system and predicting the rate and effect of climate change on our home planet. In fact, the vegetation on land and in the oceans are a crucial component of the global carbon cycle and climate change science. Plants are the real lungs of the Earth, absorbing the carbon dioxide from the atmosphere and producing the oxygen that we breathe. Here we see what's called net primary productivity, maps of where and how much carbon is taken up or released by plants on a monthly basis. The colors on these maps indicate how fast carbon was taken in for every square meter of land. And you can see how most of the change in carbon uptake and emissions happens in the northern hemisphere, where a majority of the land masses lie. Maps such as these allow us scientists to routinely monitor plants' role in the global carbon cycle and monitor how they're affecting and affected by our changing climate. Carbon is emitted into the atmosphere from natural sources, such as forest clearing, decomposition, or volcanic activity. 90% of the non-natural emissions result from power production, cement production, and transportation. Over time, 50% of that carbon that's emitted stays in the atmosphere, while 25% gets taken up by trees and plants, and the remaining 25% is taken up by our oceans. And in fact, we can measure the contribution in vegetation growth and humans' emissions on the carbon that is stored in the atmosphere using satellite data. So this visualization is a time series of the global distribution and variation of carbon dioxide in the atmosphere as observed by NASA satellites since the year 2000. For comparison, we've overlaid a graph of the seasonal and interannual increase of carbon dioxide that was measured at the Mauna Loa Observatory in Hawaii. So these data sets show us that the amount of carbon dioxide stored in the atmosphere is steadily increasing as we continuously pump carbon into the atmosphere and decrease our forested and vegetated areas. And even though we still see that semi-annual dip in concentrations with the growth of vegetation in the springtime, the increasing trend in carbon dioxide concentrations is leading to the warming and changing of our planet. The seasonal pulse of vegetation growth is crucial for the well-being and balance of life on Earth. This visualization of carbon dioxide concentrations in the atmosphere shows how every springtime when forests, grasslands, and agricultural lands green up, they suck up the carbon dioxide contained in the atmosphere through photosynthesis. But in the winter months, that photosynthetic uptake is not there, and the large amounts of carbon dioxide stay in the atmosphere. And in fact, data from satellite sensors have shown us that during the Northern Hemisphere's growing season, the Midwest region of the United States boasts more photosynthetic activity than anywhere else on Earth. But with changes in the distribution and type of land cover on Earth, the natural cycle of growth and carbon dioxide uptake is being disturbed, and more carbon dioxide is accumulating in the atmosphere. Forest fires are one of the leading causes of vegetation change and land use change emissions globally. But the cause of fires can be both natural or human-induced. In Africa, forest fires are used to clear land for agricultural activity, and the amount and timing of fires is clearly linked to the seasonal changes from healthy green vegetation to dry grasses, leading to these sweeping waves of fire that move from south to north and north to south each season. As these areas are getting hotter and drier with climate change, the intensity and amount of fire increases, leading to even more clearing. But our satellite sensors don't just show us the health and changes in vegetation on large scales. We can also monitor the human impact on our planet on the scale of a city or a neighborhood. So this image series shows us the massive growth spurt of Las Vegas since 1972. Those large red areas are actually green spaces, such as city parks or golf courses. But now take a look at Lake Mead. We can see how, with the influx of people into the area, the water table is steadily decreasing. These images from Landsat really show us how we humans have changed our planet. Here we see the impact of mountaintop removal in West Virginia from 1984 to the present. In Saudi Arabia, we're able to see how irrigation technology has led to agricultural expansion in deserts, but also to water table depletion in nearby reservoirs. All of these examples are showing how we humans are changing the look of the planet and consequently significantly affecting its vital signs. Our last example shows a recent map of forest cover loss that has highlighted the extensive changes happening since just the year 2000. These images show forest clearing from wildfires in Colorado from 2000 to 2012, fueled by record temperatures and dry conditions. In general, wildfires in the western United States are increasing in frequency and duration due to higher temperatures and longer growing seasons. And this has resulted in twice as many acres burnt each year compared to just 40 years ago. These seasons are like the heartbeat of the planet, fueling the growth of vegetation worldwide. And just as the seasons can affect the health of forested areas, they're also affecting the health of our ice caps and glaciers. And on that note, I would like to thank you for listening and introduce the next speaker, Dr. Torsten Marcus.
Good evening. Thank you, Lola. And before I start, I just wanted to say that Lola, a couple of years ago, won the Presidential Early Career Award in Science and Engineering. Super honor. Congratulations. I think it's really cool. So anyhow, yeah, we have good people that got it, in case you haven't noticed. So now let's get to the cool part of this evening. The ice, or we scientists call it lovingly the cryosphere. Or we use fancy words, to make it sound better. Now the bad news for the ice, the Earth is getting warmer. And that's just a fact, and no matter what you think about global change, global warming, etc., it is getting warmer, and it's most pronounced at polar latitudes. It's especially true for the Arctic. We at Goddard, we at NASA, I should say, we like to include JPL sometimes. We at Goddard, and at JPL, study the Arctic from satellites. It's a very hostile environment. It's only with, with satellites that we have, now a data record of what's going on in the Arctic. And at the graph behind me, you see, the temporal evolution of Arctic sea ice during the summer. In the early years of passive microwave satellite imagery, it was relatively stable, and scientists detected a slight decrease in sea ice extent. But over the last years, this trend has increased. The negative trend has increased tremendously, and there's absolutely no doubt anymore for many scientists that the Arctic sea ice is shrinking tremendously. These trends are statistically significant. To understand better what's going on, we need to understand that the Arctic sea ice, it's completely different from a frozen lake that in your neighborhood. It's a very highly dynamic system. It moves around, and like a pulsating living being. And you can see, for example, west of Greenland and especially east of Greenland, these big streams, currents of thick ice that is leaving the Arctic system. And it's way more than, as I said, a frozen lake. There are constant openings and closings. And it's in these openings where the heat from the ocean is getting into the atmosphere. It's a very complex system. It's very beautiful too, I have to say. And this is why it's so complicated to do predictions. And if I could do predictions, I would become a stockbroker. So, as the ice is shrinking and thinning, it's more, subjective to changes in atmospheric and oceanic conditions. The record minimum we observed in 2012 is largely driven by the storm that developed over the Arctic that moved a lot of ice out of the Arctic Ocean. And so we are seeing these interactions between ocean, atmosphere, and ice more dramatically than we had seen in the past when we had a more consolidated ice pack. If you go to the next slide. So we see this drastic change in the Arctic. On the other side, you see the Antarctic. And people noticed, hey, what's going on? The Arctic is changing. The Antarctic is not changing as much. As a matter of fact, we see a slight increase in the Antarctic. The reason is these are completely different beasts, completely different climate system. For example, just to say one example, in the Arctic, at the North Pole, we have ocean, which is surrounded by land. So the opposite is true. In the southern hemisphere, we have a land mass, which is surrounded by ocean. And talking about land masses, similar to the sea ice, the ice sheets are dynamic as well. Again, it's not just a stable ice sheet. The way ice sheets work is it snows at the center of the Arctic, of the ice sheet, Antarctica or Greenland, and this ice is slowly moving towards the edges of the continent and breaks off as icebergs. And if the system is in balance, the mass of snow equals the mass of the icebergs that are breaking off. In addition to this, though, we have see increased melt. We had a record melt in Greenland a year or two ago. And in addition to melt itself, we know that some of the meltwater that accumulates as ponds on top of the ice can drain to the bottom of the ocean, to the bottom of the ice sheet, and lubricate the interface between the ice sheet and the bedrock, causing an extreme acceleration of glacier flow. And some of the glaciers, especially around Greenland, accelerated by more than 100%. We have satellites that can actually directly measure the mass of the ice sheets. One of the coolest concepts, I mean, as a physicist, I think it's a really cool concept, is GRACE. And GRACE doesn't look upwards or downwards. It actually just measures the distance between itself, between the two satellites, and that with a precision, with less of the width of a hair. And as the first satellite goes over a field of high gravity, it's accelerated ever so slightly, and the distance between these satellites increases until the second satellite is over the same gravity hill, and the distance becomes equal again. So using results from GRACE, we can actually determine directly the mass of the ice sheets. And if you look at the time series of derived from GRACE over Greenland, we can see we have tremendous, tremendous losses. We are losing right now about 200 gigatons of ice every year. So I can, to provide an analogy, it's a kilometer by a kilometer by a kilometer of ice is 1 gigaton. Or 200 gigatons, I did the math on my way out here. 200 gigatons of ice, would cover the state of California roughly with half a meter. So every, we can add half a meter every year for California. If Senator Nelson would still be here, it's almost, equal to the area. I think it's close to the equal area of Florida. And then we launched ISAT-2 and ISAT-1, sorry, in 2003. This was the first laser altimeter that surrounded Earth, and we got a much better view in terms of how is the elevation changing around Greenland, around Antarctica, and it provided the first measurement of the Antarctic as well as the Arctic sea ices. Before then, we were pretty much blind of this third dimension of the ice sheets and the sea ice. So it was a real cool mission, and very NASA, I think. ISAT-1 ended in 2009, and after that, we started a campaign called Operation Icebridge. The scientists, unfortunately, as well, headquarters as well, realized we cannot afford to be completely blind to the fast-changing, conditions in the climate regions. So we're flying twice a year, over the key regions in the Arctic as well and in the Antarctic. And instead of showing more data, I thought, let's look just at some of the pictures, because it's, I had the honor and the privilege of flying on some of these missions. It is just phenomenal flying over, it's 1,500 feet, 500 meters, it's really close, flying over the ice sheets and sea ice. And you fly over a glacier and you have mountains left and right. And in addition to lasers, we have radars that penetrate the ice, so we can actually measure the ice thickness as well. And then, of course, with all the objectivity of a project scientist, in 2017, we will launch ISAT-2, which is so cool and so phenomenal. And it's this is NASA at its best, in my opinion, because it's, groundbreaking technology and groundbreaking science. With ISAT-1, we measured, the Earth every, 150 meter, roughly, if you think about football seasons are started, basically, in the end zones. With ISAT-2, we measure with centimeter precision, every yard line, which is really cool. And, it will be really a really discovery mission. And in addition to monitoring the ice sheets, we will monitor the heights of trees, changes in land, maybe tectonics, heights of the oceans, etc. It will be a real discovery mission. I'm very, 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 very excited about it and work very hard. When I was a young scientist, this is my last slide, just 10 years ago, I went to Antarctica to measure sea ice thickness. This was then, 10 years ago, before ISAT-2 launched, the only way we could measure sea ice thickness. There was no other means. We went there and drilled, lots and lots and lots of holes. It was great fun, of course, and we had some visitors as well, as you can see in the top, what is it from your side? Top left. Isn't it amazing to just come out and look what we're doing? So, you know, I think NASA does really cool stuff for cryospheric scientists, and we have come a long way since, 10 years ago when I went down there to take measurements of the ice. And with this, I want to give the microphone to Pierre Sellers, former astronaut and my boss.
So I have to treat Thorsten with a lot of respect because he reminds me of Arnie Schwarzenegger with a PhD. I don't want to get on the wrong side of him. So, okay, the view from orbit really does put things in perspective. And Senator Nelson has seen this with his own eyes, so he knows what I'm talking about. And I've enjoyed seeing the Earth too with my own eyes through a spacesuit visor. And I'm absolutely fascinated by what our satellite instruments can tell us. We, that's NASA and all our friends of NASA, are quite literally conducting a health check of the planet. Okay, so these hands-on working scientists have dazzled with facts and data. It's my job as a grizzled bureaucrat to drag this event over the finish line and let you find your cars. So I'll try and be quick. So here are a few closing thoughts on what all of this means for science, for policymakers, and for the crew of Spaceship Earth. That's all of us. Okay, this movie shows you what happens when we combine the satellite data with computer models and use the laws of physics to fill in the gaps between observations. Here we are out in space. This is not a snowstorm. These are solar particles blasting by the Earth, but we're protected by a magnetic field. So the particles are diverted. As we come down deeper, by the way, this is a model based on physics and observations, so there's fact and mathematics. Isaac Newton's hard at work here. Here's the atmospheric flows, again produced by a model. Circulation, time scales here are on hours to days. So we come a little bit deeper into the world. We see the surface winds, and now we're looking at the surface ocean circulation. As Gail said, that's forced by heat, wind, and salinity. Time scales of days and months and years. Deeper yet, and now I'll talk with the French accent, like Jacques Cousteau, the subsurface flows down to the deep ocean circulation. Time scales of 1,000 years or more. It's beautiful. And we get all of this for combining the satellite data with what we understand about nature and putting it into a computer. And this stuff is based on actual reality, not the Kardashian kind. But let's get back to thinking about climate. So here's a computer model simulation of the Earth's climate system. This is not a picture, this is a simulation. It's a toy world based on physics and propelled by satellite data. Now I just want you to look at the detail here. The popcorn clouds, the winds, or the planetary scale waves in the atmosphere, the snow, the ice, the biosphere, it's all right there. It's all being calculated and it's all being faithfully reproduced. Well, what is this all good for? Well, models have got to the point of providing weather prediction out to 72 hours reliably. You can quite literally bank on it most days. This is going to be Hurricane Sandy. This is actually a model prediction of Sandy. And as you can see, the hurricane wandered around the Atlantic before turning sharply left and whacking New Jersey and New York. But accurate warnings were given out 72 hours ahead of time, and many lives and a lot of money was saved as a result of these warnings. And by the way, speaking for us, that's not counting all the people up and down the East Coast who did not have to evacuate because they knew the hurricane was going to miss them altogether, and that counts for something. Now, the exact same physics and many of the same observations that we use for weather are helping us to understand climate better. And these climate models allow us to peer into the future and will help us make decisions about energy, water, and food resources. Okay, this is a simulation of what we think the Earth will look like in 20 to 30 years. Actually, it's not. It's a picture of the sun that's been taken by our heliophysical friends using their satellites. And besides being a really cool image, it shows that we're keeping a close eye on the sun, again using satellites. And guess what? We have found the sun to be not guilty for the recent warming trend. Now, as I said, we use the same exact physics and many of the same satellite data that we use in weather models to build and test our climate models. And what these models do tell us is that the rate of warming depends very largely on how much fossil fuel we use and how much carbon dioxide we put in the atmosphere. I'm now going to show you a graph. I know it's very bad form for an evening like this, but in compensation, it may be the most expensive graph ever made, and that's not because of the colors. This cost several years of effort by thousands of scientists worldwide to put it together. And it tells us something we didn't know until only recently. It's something new, and it's something very, very simple. What it says is that the expected rise in temperature is directly, linearly related to the amount of fossil fuel we burn. The x-axis at the bottom shows how much fossil fuel we burn, which makes it carbon dioxide. And the y-axis shows the temperature increase that results from this extra CO2. And the 0 point is roughly, or a bit left of the 0 point, is roughly when some fella in England in 1700 decided it was time to start an industrial revolution and dug up the first bit of coal. Now, if you look at the black line that ends at 2010, you'll see that we've burned about 500 gigatons of carbon since then. And a gigaton of carbon is a brick of coal about a kilometer on the side, so it's a big piece of coal. And that gives us about a 1 degree centigrade rise in global temperature, which is what we've seen. And that's led to some of the changes in the world that my good friends have just shown you. Now we're likely to burn 1,000 gigatons. That's halfway up the graph. That'll give us 2 degrees centigrade to 2.5 degrees centigrade increase in global temperature. We definitely don't want to be up in the top right-hand corner, 4 degrees centigrade. This would look like a very different planet than the current Earth we inhabit. And we don't really know what that planet would look like or how it would work. So this is sobering, right? But is it necessarily going to be grim and nasty to the maximum? Is this evening going to be a total downer for you all if we don't count the refreshments? I think not. And there's some basis for my optimism. Here's a picture of the ozone hole that was discovered in 1979. The blue color shows that the ozone is being eaten up by man-made chemicals, mainly refrigerants. And we saw the hole growing rapidly in the 80s and 90s. And this was bad news, because ozone protects most of life on Earth from strong ultraviolet radiation from the sun, and that's bad for you. But here's the good part of the story. Governments all around the world took the information seriously. Here's a UN meeting where they're discussing the problem and what to do about it. It's modeled on a Goddard seminar. And here's all the agreements that they cranked out to reduce the chemicals that caused the problem. And here's 2 of Goddard's finest scientists in the back row providing solid science advice and eating chips. There they are. All right. And what happened? Here's a picture of 2 worlds. On the left is the world that we are likely to see, with the ozone depletion leveling off and then slowly reversing. And on the right is what would have happened if we didn't have all those controls and agreements. And blue here means no ozone, which is bad news. On the right-hand side is the world we avoided. That's a world with thinning ozone, a world with damage to all living things exposed to sunlight, and that includes the crops that provide our food, the ocean plankton that makes our oxygen, and damage to us people. And now a news flash. Today, at 4 o'clock, the United Nations released a statement. It reads, "The Earth's protective ozone layer is well on track to recovery in the next few decades, thanks to concerted international action against ozone-depleting substances, according to a new assessment by 300 scientists." So, it can be done. This is proof that people, and that's all of us and our political representatives, can use solid information, facts, models, like everything we've seen tonight, to make the right decisions. Now, sometimes it happens a bit later, and it takes a bit longer than we would like, but generally, the right decisions get made. Now, there's a lot of people on this planet. This is Christmas 1968. 3 billion people on Earth, and there they all are. Actually, we, or some of us, are -3 because somebody had to take the photo. Now, here's a picture 2013, put together from satellite data. Now there are 7 billion of us, plus 6 on space. And we will top out at about 9 billion this century. But again, I think there's reason for optimism here, because people are actually part of the solution. Every new human born is not just an extra stress on the world, but brings with himself or herself resources and answers. This is an early picture of Len Fisk. So I hope that with the ingenuity, the resourcefulness, the grit that has got the human race so far, we can use these vital signs about the health of our planet to figure out how to live long and prosper on this earth. Now, before I close up, I'd like to recognize the great work done by the visualization team, Ali Ogden, Wade Sisler, Ronnie Grant, Horace Mitchell, and friends who put all these beautiful pictures together. And of course, a huge thank you for all the speakers and sponsors. So put your hands together, please.